what we are going to first of all cover, what different types of pumps are there
Chat.
actually.
You can click on the hide button.
Yeah, that's okay. It is necessary for the recording purpose that I'm sharing the screen. There is no any content there, so that won't be an issue. Okay, so what we are going to first of all cover that we are going to cover the introduction to pumps quickly, and after that, sequentially, we will see what actually are the curves, right? So, a basic example we will solve. You all will be solving. I will be giving the questions, right? Some values I will be giving. Based on that, you will be calculating, and we will see whether you have understood the concepts or not. After that, we will go for hydraulic calculation, which is also known as head calculation, right? So basically, what actually is a pump? So we all know that a pump actually is a mechanical device which is used to give energy to a flowing liquid. Like it can be any liquid, so that the liquid can overcome the resistance in the hydraulic system. What actually is hydraulic system? A hydraulic system is basically uh, your complete plant system from a point where you are, which is called a suction point, and a point which is called a discharge point. Means from the start, from source to destination, complete system, whatever is there in that part. It may be some control valves, it may be valves, it may be strainer, okay, it may be horizontal pipelines, it may be a vertical pipeline. So complete system is called, this is called a set of systems, right? So this is known as hydraulic systems, which cover a source, a destination, a pump which is transferring your fluid from one place to another, which is doing a suction from your source and discharging wherever you need it in the plant, right? So simply, what a pumps do, pumps convert mechanical energy into hydraulic energy given to the flow. Okay, so there are many applications why we are using pumps. Earlier history of pump is like that. It was earlier used only for water transferring. This is the history of pump. It was earlier used only for watering of pumps. Do everyone know the unit MWC? Is anyone aware of the unit MWC? We will keep it
Meter
a,
water column.
yeah, we will keep it a two-way conversation. Okay, so in in between I will be asking some questions so that I can understand that how to take the flow of this lecture, right? So meters of water column. So meters of water column was derived at that time when the pump was only used for water transferring. So that is kept as a base. Even when you do a head calculation, you always took two densities. One density is of the fluid which you will be transferring from one place to another, and another density which you will need for the calculation of pump hydraulics is water density, because it is kept as a relative reference. So we will see that thing in pump calculations, right? So basically, if we talk about applications, what actually are pump applications? So pumps are actually used or found in numerous applications in industry, right? So it might be using for pumping oil and petroleum derivatives from production or storage site to the market. Okay, so it might be like you're using pumping for drinking wastewater, okay, to or from homes. You might be using it for cooling water pump, you might be using for firefighting applications. So pumps are used for various applications. So basically, what actually are pumps? Pumps are basically divided into two categories. One is PDP and the another is DHP. What actually is PDP? PDP is positive displacement pump, and DHPs are dynamic head pumps. PDP are usually common, which are known to everyone, but the term DHPs are not commonly used. Usually, everyone knows that positive displacement pumps are there and centrifugal pumps are there. But centrifugal pumps fall in which category? So it is DHPs, dynamic head pumps. So PDP, positive displacement pumps, in that we have two categories. One is reciprocating and the another is rotary. Right. In reciprocating, we will be having a piston types, and in rotary, gear types pumps falls. And in DHPs, we have a single centrifugal pump. So moving forward, I'll be just moving the slide what we have introduced. So the main two categories of pumps are there: rotodynamic and positive displacements. Rotodynamic means DHPs, dynamic head pumps, right? And the positive displacement pumps, which are having again divided into two categories. One is rotary and another is reciprocating. So in rotary, we have gear pumps, lobe pumps, sliding vane pumps, screw pumps. There are different types of pumps available in the market. Usually, gear and lobe pumps are used in the category of rotary in industries, right? Screw pumps are used very. Screw pumps are not used very frequently. It is generally used for specific purpose where the solid contents are quite high in the liquid, right? Means if it is not a solution, if it is a slurry, then screw pumps are used because centrifugal pumps can get damaged. Everyone are aware of the difference between solution and slurry. What actually is the difference? Because these terms are will be used frequently in this lecture. So, do you know the difference between solution and slurry?
No, sir.
Anyone else who knows?
Some it would contain a certain percentage of solids along with the liquid. Then we can say it is a slurry. But
Okay,
solution means the solute is completely dissolved and it's homogeneous. There is no heterogeneous phase presence in that.
right, right. But one thing I would like to add, but solid is also present in solution, but it is in a
Yes.
dissolved form, right? If you what happens sometimes, if we have a solution and if you decrease the temperature or if you evaporate some of the solvent or whatever liquid is there, so you will be seeing that the solid deposition or precipitation starts. Some operations are there where you need to evaporate the solvent, right? And as the solution in the solution, as the solvent is removed, it reaches the saturation point where the solid which have been dissolved is now not dissolved. It starts precipitating and agglomeration is done. So what actually is the difference between solution and slurry? So both contains solids, but as one of my friends says here, that it is a homogeneous mass. Solution is a homogeneous mass and a slurry is a heterogeneous mass where we have a certain solid percentage which is not dissolved. Okay, in slurry, a certain solid percentage is there which is not dissolved. It is in a suspended form, or it might not be in a suspended form, but it might be precipitated in the vessel. Okay, so this is the basic difference between solution and slurry. So if the solid is in dissolved form, means if we have a homogeneous solution, then you can use centrifugal pumps and all. See, basically in the pump categories, 90% of the time, what you will see in a chemical industries, that 90% of the time, usually centrifugal pumps are used. Why? The reason is centrifugal pumps are most widely used because of its high operating range. Okay, how it has high operating range, that we are going to understand through the system curves and pumps curves. So you can operate it at various flow, you can operate it at various heads. So this is the beauty of centrifugal pumps, right? So if you have a solution, but if some evaporation is done, like if you have another mass which is a slurry, which is in slurry form, means you have a solid content higher than the saturation point. So in that case, centrifugal pump won't work after a certain limit, which is around 10 to 20%. Okay. So after that, what will happen? The solid parts can trigger or it can hinder your operation of centrifugal force, because the impeller of the centrifugal pump can get damaged by the force of suction. Okay. So in that case, centrifugal pumps are not used. So in that case, we use screw pumps. So screw pumps are used around 2 to 5% in the chemical industry, where you are transferring slurry in some cases, right? So usually 90% of the time you will be using centrifugal pumps. So this was the basic category. So let's move ahead. So we have discussed this. What actually is a pump? The pump increases the mechanical energy of the liquid. Okay, the pump increases the mechanical energy of the liquid, increasing its velocity, pressure, or elevation. It is the devices which is used to transport, move liquids through pipes and channels. We have two categories: positive displacement pumps and centrifugal pumps. Reciprocating pumps, we have piston, plunger, and diaphragm. And in rotary pump, we have gear, screw, lobe, and vane. Okay, so in gear, we have internal gear pumps and spur gear pumps, means external gear pumps. So these are the basic categories. So for centrifugal pumps, what actually is a centrifugal pumps? See, centrifugal pumps fall in the category of DHPs, which is dynamic head pumps. So there are three main performance difference between the two pumps. So DHPs, which are called dynamic head pumps. Whenever I'm talking about dynamic head pumps, it is basically a centrifugal pumps. Okay, so they provide a smooth continuous flow. Okay, here we have. You can read it while I'm explaining. This is two difference between centrifugal and positive displacement pump. What actually is the definition of centrifugal pumps and what actually is the definition of positive displacement pumps? What we are going to understand is what basically is the difference between these two. So centrifugal pumps provide a smooth continuous flow, while your positive displacement pumps have a pulse with each stroke. Why? Because positive displacement pumps have piston and plungers. So what happens in positive displacement pumps? You won't get a smooth continuous flow. Your flow will be hindered. Why? When the piston is, how is the piston moving in positive displacement pump? It is moving horizontally. So when it is moving horizontally on the left side, so at that time the suction takes place but the discharge is stopped, and when the piston or plunger moves horizontally again to the right side, so at that time the suction is stopped and the discharge is started. So that's why you have a pulse with each stroke or each time a pumping chamber opens to an outlet port. So what will happen? Pressure can reduce a DHP's delivery. Pressure can reduce a DHP's delivery means in centrifugal pumps, pressure can reduce, but high outlet pressure can stop any output. The liquid simply recirculate inside the pump. Or what happens in PDP is completely different. The pressure affects the output only to the extent that it increases internal leakage. Means what actually is the difference? If you are having one centrifugal pump and if you are having one positive displacement pump, okay, let's imagine you are having these two pumps and you have installed one valve on the discharge line of both pump. Okay, and you you have completely closed the valves on the discharge line for both the pumps and you have started pumping. So what will happen in both cases? Will pressure increase in both cases?
Only positive displacement pressure will increase.
Increase.
Centrifugal pump will not increase. Yeah.
Okay. Anybody else? It will increase in centrifugal
In
pumping
a
area.
positive,
Yes, yes, you can tell.
i- yes, in positive displacement pump, the pressure increase tremendously is very much. So we require PSV on outlet because in performance curve of positive displacement, it is a vertical line between head versus flow rate.
Right. That is correct. So what happens actually in centrifugal pumps? In centrifugal pumps also the pressures are increased, but up to when? Do you know the term shut off?
Shut off head. Shut off head.
Right.
Yes.
So if you have closed the discharge valve, right? If you have closed the discharge valve on the centrifugal pump, what will happen? It will only increase the pressure till the shut off head, which is respective to the shut off head. But it is not same with positive displacement pumps. In positive displacement pumps, if continuously the stroke is happening, so it will increase the pressure continuously, right? So if your positive displacement pump casing is not designed for that higher pressure, and if your pipeline is designed for higher pressure, so your casing will get burst. If your casing is designed for higher pressure but your pipeline is not designed for higher pressure, so your pipeline can get burst. So what one of my friends says here, that we installed a PSV. We don't install PSV, is actually pressure safety valve, which is used for the protection of our any equipment, whether it might be a vessel or it might be a pipeline. So PSVs protect our equipment from overpressure. Okay, so you do not require to install PSV on the discharge of centrifugal pump, but you should always install a PSV on the discharge of positive displacement pump. So you have to give the set point based on what you're operating, or based on the pump curves what your operating point is there. So considering that point, you need to give the set point to the PSV, like it might be a 10% excess or 21% excess based on what case you're designing your PSV, right? So moving ahead, this was the difference which we learned basically between kinetic and positive displacement pump. So kinetic pumps are dynamic head pumps, kinetic pumps, centrifugal pumps, these are all same. Okay. The kinetic pump imparts velocity energy to the fluid, which is converted to pressure energy upon exiting the pump casing, which is centrifugal pump. A positive displacement pump moves a fixed volume of fluid within the fluid casing by applying a force to movable boundaries containing the fluid volume. What we understand with an example, that when your plunger or piston moves to the left side, the suction happens and the discharge is closed. The discharge doesn't happen because that force is not there to move the fluid outside and to perform a discharge, right? So when the piston is moves on the left side, the suction happens and the fixed volume, what the term here fixed volume means, see, if this is your casing, this is your piston, this is your fixed volume. In positive displacement pump, you will get the amount of fluid inside the casing only what actually is the volume of the casing, right? So you are getting the suction, you are, if the suction is filled, then the piston will again move forward and the discharge will happen, suction will be closed. So this is how a positive displacement pumps work, by transferring a fixed volume of fluid within the pump casing. So positive displacement pumps actually displace the fixed amount of liquid from suction side to discharge side. So what we learn is this pump gives very high pressure, but they give very little flow rates. Why they give very little flow rates? Because they're having a fixed volume of fluid within the pump casing. They can't supply you higher flow rates like centrifugal pumps, because centrifugal pumps is continuously taking suction and it is continuously discharging your fluid wherever you need it in the plant, right? So these are the basic difference. So in positive displacement pumps, what we have is two category: reciprocating pump and rotary pump. So in reciprocating pumps and rotary pump, what happens in reciprocating pumps, there are piston and plunger. What we were talking about, one is piston and plunger. In piston, what we have, a hollow shaft is there, which is connected to a rectangular bar. So this is a piston which is moving horizontally left and right, and this is a plunger where it is not a hollow shaft, it is a complete bar, okay, but of higher diameter. So it is only moving your fluid. The plunger is itself moving your fluid, and the plunger itself is used for the suction and discharge. So it's only a geometry difference between piston and plunger. The applications and purpose and the principle of working is completely same. But what happens in rotary pumps? In rotary pumps, the chambers move from inlet to discharge and back to the inlet. So what actually is rotary pump? We have gears inside the rotary pumps. So two gears are rotated based on which you get the inlet and you will have a discharge. In this, you will have a continuous flow, but still the pressure will be increasing in the discharge side because it is a positive displacement pump. So this was reciprocating pumps and rotary pumps. So if we talk about what we discussed about piston pump, that liquid is drawn through an inlet check valve into the cylinder by the withdrawal of a piston. Then the liquid is forced out through a discharge on the return stroke. This is single acting piston pump, which is you are seeing here. See, you are seeing the arrow. When the piston is moved on the right side, this valve gets open and you will see a discharge. Right, this is a check valve which is open and you will see a discharge. And when it is moving on the left side, means in a backward position, this valve is closed. The discharge doesn't happen, and this check valve gets open, and you will see what you will see, that you are getting suction, right? So discharge is completely closed, the check valve of suction side opens and you get the fluid inside the cylinder of piston pumps. So this is how a piston pump looks in the industry. From outside, this is the piston pumps, how it looks. Okay, this was a 3D section diagram. This was a 3D diagram, and this is how actually the pump looks. So first of all, what we saw was single acting piston pump. Here we are seeing the double acting piston pump. Double acting piston pumps mean at the same time you will have suction, and at the same time you will have discharge. So see, here when the piston is moving forward, so your check valve for discharge side is open, you are getting the discharge, and the check valve of this suction side is open and you are getting the suction. And when it gets back again, so the discharge side of this side is open and the suction side of another suction side is open. So in double acting, what happens? You are having two suction sides and you are having two discharge sides. So at every stroke, the cylinder will be filled. Certain amount of fluid will be filled inside the cylinder, and the certain amount of fluid will be discharged at every stroke. So this is a double acting piston pump. This is a 3D diagram. These two are discharge points. These two are suction points. This is a piston. Okay. So this is a double acting piston pump. Now a plunger pump. Plunger pump, what we have seen, that you have a discharge point, a chamber. Instead of piston, you have only a plunger. The basic difference between piston and plunger is you have seen that in a piston pump, you have a small rectangular bar which is connected to a hollow straight bar. But here you have a plunger which is not a hollow bar but a complete cylindrical bar which is filled with metal. Okay, so it can generate higher pressure. What we are seeing in piston pump, that piston pumps can generate a maximum discharge pressure of about only 50 atmospheric. But what happens in plunger pump, it can generate the discharge pressure of around 1500 atmospheric. So this is only the basic difference between piston and plunger pump. Rest everything, operation point of view and from application point of view and from working principle point of view, both are same. Just the difference is that it can discharge higher pressure. It can generate higher pressure at discharge of around 1500 atmospheric. So only your safety point of view, you have to look into that of what size your PSU will be size, which pipeline you have to select. You have to select higher rating pipelines, right? So these are the difference you have to look upon. So this is the plunger pump, motor driven, right? This is your discharge point, this is your suction point, and this is the plunger which is connected to the motor. This is a cylindrical part which you are seeing, complete metallic. It is not a hollow. Another pump is diaphragm pump. What happens in diaphragm pump? You are having a, here the reciprocating member is flexible diaphragm. Instead of plunger or piston, you are having a diaphragm. So the diaphragm is a flexible material. Okay. Diaphragm pumps you won't see usually in chemical industry. Instead, you will be usually seeing AODD pumps. Anybody know AODD pumps?
Air operated
Air
Air
operated double.
operated.
Right. So air operated double diaphragm means it is having a double diaphragm inside it. So it is operated based on air. The air, what your discharge pressure of air is there, based on that only your fluid is delivered, right? If you are having a highly flammable liquid, in that case, can you use air operated double diaphragm or AODD pump?
No, due to oxygen content in it.
Right. So there are certain limitations. What I want to make you understand, that there are certain limitations of diaphragm pumps. Usually the chemicals which are used inside the chemical industries are highly flammable. If it like make a contact with air or oxygen, so it can generate flames. Okay, it can burst. So in that case, we usually avoid AODT pumps. But if you are having a general solvents, if you want to transfer general solvents or thick fluids, which are, if you are having the MSDS of, I think everyone is aware of MSDS, material safety data sheet. So for every chemicals you are having MSDS. So for, if you are having MSDS, you know each and every values, that where your chemical falls, your chemical is safe to handle through air. So in that case, you can use diaphragm pumps. So generally, diaphragm pumps are used for low flows up to 100 gallon per minute. Okay, so it is only used for low flows. Centrifugal pumps can give you enormous volumetric flow rates compared to this diaphragm pump, but it is generally used for low flows, because centrifugal pumps won't operate and it won't give that efficiency at low flows if we compare it with the diaphragm pumps. So basically what we want to understand is that diaphragm pumps handle small to moderate amount of liquid up to about 100 gallon per minute. It can develop pressures in excess of 100 atmospheric. So this is how a diaphragm pump works. This is basically a motor operated diaphragm pump. This is your diaphragm. Okay, this is your inlet, this is your discharge, and it is connected to a rotor. So this rotor will be connected to a motor based on which your diaphragm pump works. So now what we are talking about is rotary pump. Unlike any other reciprocating pumps, rotary pumps contain no check valves. Means you are not having any check valves. It is completely filled. Where we use check valves are used where we don't want a reverse flow, where you want only one-sided flow. But if you are having rotary pumps, there is no need of check valves. What we saw here, in piston, you are having check valves. Here it is check valve, here it is check valve, here it is check valve, here it is check valves. In piston plungers, you have check valves. In diaphragm also, you have check valves. Here it is check valves, here it is check valves. But in rotary pumps, we don't have any check valves. What we have is only a chamber where we have gears. So it completely transfers your fluid from one place to another point. Okay, so it minimizes leakage from the discharge space back to the suction space. Okay, so they also limit the operating speed. So discharge pressure are up to 200 atmospheric or more. It means up to 250 it can attain, but it is under discussion. It is still under discussion. But what industries have seen that a rotary pumps have generated a discharge pressure up to 200 atmospheric, not more than that till now. In certain cases, in one or two cases till date, like in several, you might be knowing Indraprastha refinery in Panipat. Do you know Indraprastha refinery in Panipat?
No, sir.
So there was one refinery in means there is one refinery in Panipat which is known as Indraprastha refinery. There was one case happened there that they were using a rotary pump and they were expecting that it will not deliver a pressure higher than 200 atmospheric. So what they did the designing of pipelines of discharge side consisting of 220 atmospheric. So they did the designing of this pump casing or this chambers with the 220 atmospheric, but that rotary pump gave them a discharge pressure of around 325 atmospheric. So that was one case. So it is still under discussion why it did happen. So but the reports have not been yet released. So that's why the term or more here it is written, but it was not written in any other pump. So still discharge pressure up to 200 atmospheric can be attained by rotary pumps, right? So here in rotary pumps you have spur gear pumps where the gear is inside. Okay, if the gear is vertically mounted, so it looks like this, and if it is horizontally aligned, so it looks like this. So the inlet is here in the horizontally aligned and the discharge point is here. And when it is vertically aligned, so you have an inlet point here and the discharge point is here. So liquid entering the suction line at the bottom of the casing is caught in the spaces between the and the casing. It is carried around to the top of the casing and forced out the discharge. So this is how the spur gear pumps work. Sorry. So this is a pictorial representation of what we saw earlier. So what you are seeing, the red part is the suction part, how the suction fluid flows and it goes to the top of the chamber between the teeth, and then it is this blue part is your discharge part. So and now the discharge happens. So this is how the spare gear pumps work. Now what we are having is internal gear pumps. You won't have seen this internal gear pumps in any fluid transfer operations, I believe. So its design is quite complicated and which makes it an interesting gear pump. So what actually is difference in design? So you have a crescent moon. In this gear pump, you have a stationary part and you have a rotary part, both. What we saw earlier in gear pumps that you have both rotary parts. Both are in the rotary motion. But what you will see here that you have two gears, right? This is ring gear, okay, and this is your pinion. So these both are rotary parts, but one you have a crescent. It has what is actually a crescent, a moon-like structure on which the pinion is placed, and this you have a ring gear. So you can see the ring gear is connected to the pinion, right? So a spur gear or pinion meshes with a ring gear with internal teeth. So it is connected with the internal teeth. Both gears are inside the casing, but the ring gear is coaxial with the inside of the casing, but the pinion which is externally driven is mounted eccentrically with respect to the center of the casing. So how does it work? Can you see the center part? This one at this point. So this center point, you have the shaft. So this shaft is connected to the motor, and this pinion is rotated with the help of electrically driven motor. And once this pinion is rotated, and based on the force of this rotation, your ring gear gets rotated. So the fluid moves inside this and it gets flow from the crescent moon of here and from this part, and then it gets discharged. So liquid is carried from inlet to discharge by both gears in the spaces between the gear teeth and the crescent. So why this design has been formed? What would be the reason of this? Because you have this gear pump, so why to use this? So when it is used, generally it is generally used where you have a solid concentration of more than 20%. So what will happen if you are having a higher solid concentration here? If you are using the higher solid concentration here, you will see that the solid gets deposited here at this point, 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 at the complete chamber. You will see that the solid it gets deposited, and then the cleaning and maintenance work of this per gear pumps is quite risky. So you have this design where the solid concentration will only be deposited on the ring gear side. Okay, as the distance or clearance between the pinion and the crescent moon is quite low, the solid won't get deposited here, but the solid will get deposited here, whatever the deposition will happen. But with the help of simply removing the casing, you can simply remove whatever the solid have been deposited. So due to this only, the rotary pump category have designed this separate internal gear pumps which have a crescent moon, the pinion, and the ring gear. Okay, so application wise it is same. It is a positive displacement pump. It will generate higher pressures, right? This is internal gear pump. How it looks, a crescent moon. This is a pure pinion. This is a ring gear, right? Here also you can say this is your pinion, crescent moon. This is outside ring gear. So I hope everyone have got the idea of this pump. I just want to know that you have got the idea of this pump, because this pump is usually not in the books. This is usually used in the industries where high concentration of solids are used. So clear with this?
Yes, sir.
Okay,
Sir, if
great.
we have caustic lye solution,
Okay,
so and I have two pumps, centrifugal pump and AODD pump, and I
okay,
have to transfer caustic lye solution from ground
okay.
floor to third floor. So which pump I have to use and why?
You can use both. See, 48% caustic lye solution, as per the solubility, it is 40% caustic lye solution. But is it homogeneous or heterogeneous?
It is homogeneous.
Right. So it is homogeneous. So you can transfer it with centrifugal pump also. You can transfer it with AODD pump also.
So, sir, I want to make sure that what is the selection criteria when industries have two pumps, centrifugal and AODD. So, why they
See,
use AODD in some cases?
if you want to transfer caustic lye solution, like if you want to dose caustic lye solution, like at a very lower flow rate, okay, at a very lower flow rate, if I would say around zero point 0.5 meter cube per hour, zero point 0.2 meter cube per hour, zero point 0.4 meter cube per hour. So you can use AODD pumps. I'm going to define a simple category. So in that case, you can use AODD pump. But if you want to deliver higher flow rates, like more than 1 meter cube per hour, 2 meter cube per hour, you can take centrifugal pumps. This is one case. But what happens, the another case is with the costing. Like for if you need to operate centrifugal pump, what you need? You need electricity, right? What happens at some places, these cases changes from places to places. Like if the first case is for Gujarat, let's say, in Gujarat area, in Gujarat industrial area, the electricity cost is quite low, so they will go for centrifugal pump. even if they want to deliver low flow rates, they are not worried about the efficiency of how the centrifugal pump is operating. Whatever
Okay. So
the
is
efficiency they will be getting, so they will selection of pumps basically happened on various categories. You need to look upon various categories. What we are going to learn here is how you will select based on categorization of fluid you are handling. But apart from handling of fluid, there are also several criteria or categories which are used in different industries from the management point of view, as they look for cost. What the industry want is profit, so they look in that category. I hope it is clear.
yeah. Is there any pressure criteria required? Like is OD pump give high pressure at discharge side where I want to transfer or
No,
nothing else?
see, there is no any criteria of pressure for selecting the pump. What you need to select, what is the basic principle of use of pump you need to transfer. If you talk about 48% caustic layer solution itself, what you need to do is you have to transfer caustic layer solution from first floor to, let's say, third floor. There is nothing pressure criteria or categorization in that, so you can simply use any of the pump. There is no any pressure criteria in that.
Density also not matter. Means if it is high dense and we have to use
Density,
OD pump then
density.
centrifugal.
See, density matters if it is having a high viscous fluid. Centrifugal pump has its own limitations. I think centrifugal pumps can handle fluids of density or viscosity around 10,000 cp. More than 10,000 cp, if you are having a viscosity of 10,000 cp of any fluid, then centrifugal pump won't work. You have to use AODD pumps. So AODD pumps are used for high viscous fluids.
And
High,
density or it is
yeah,
not there.
if it is having a high viscosity, then it will have a higher density by default.
Okay, okay, sir. Thank you.
Okay. So clear till here, everyone?
Yes, sir.
Okay. So we have one more category in positive displacement pumps, lobe pump. It is also operated in same criteria. Instead of plungers or gears, what you are having here is wooden lobe or metallic lobes or metallic lined lobes you have. Okay. So you won't see this in industries usually, but you need to understand, or you need to just know that this pump exists. Okay, this is a type of positive displacement pump, because usually in interview, if they talk about positive displacement pump, they ask what are the different types of positive displacement pumps. So you need to know that there is one pump called lobe pump which falls under the category of positive displacement pumps. Its working is same. You will get the suction from here and you will get the discharge from here. The lobe will rotate it based on the pressure of fluid you will be getting, and instead of gears, the lobe is there. It is just taking the fluid to the top of the chamber and it is discharging. The light side is called the suction side and the dark is the completely discharge points. Okay, here the dark points are suction points and the light side are discharge points. So this is how lobe pumps look like. This is vane pump. Again, the vane pump, it is only having a small impeller, but it acts like a positive displacement pump. How? Because it gives a continuous strokes. Continuously the fluid is coming with the help of impellers and vanes. It is transferring the fluid from one place to another. Again, the screw pump which we were talking about, that if you need to transfer heterogeneous mass, so you need screw pumps. So how the screw pumps look like? This is top view. This is angled view or section view, you can say. So this is your suction point. The blue line is your suction point. The screw rotates, and by rotating, it transfers the fluid from left side to right side, or it pushes the fluid in the forward direction, and the fluid is then discharged. So these screw pumps are basically used at for fluids which are heterogeneous mass or are having high solid concentration, let's say 30%, 40%, 50% solid concentration, but a heterogeneous mass. Okay, which is having, if you are, you might be having two reaction mass, one reaction, both reaction mass are having 50% concentration, but the material are different. So 150% reaction mass might be soluble, 150% reaction mass might be heterogeneous mass. Like my one friend says, gave the example of 48% caustic lye. So that 48% caustic lye will be homogeneous. But in some cases, 20% reaction mass or any other mass, it might not be soluble or let's say homogeneous. It might happen that that mass is heterogeneous. So in that cases, we select screw pump. Okay. Is it clear?
Yes.
Yes, sir.
So let's move forward to the calculation part of centrifugal pump. I will just share the screen again. Is it visible to everyone?
Yes, sir. Visible.
Okay. See, this is the basic pump hydraulic or pump head calculation sheet. Just note down the few points, note down the formulas, note down the assumptions, what you need to do while doing pump hydraulics or calculating pump heads. Okay. So this orange color, what the orange color defines, these are the inlet points. Means this inlet you need to give, these values you need to provide for calculation of pump head. Here we will understand how you will calculate pump head, how you will calculate NPSH, how you will calculate pump power. So these three things we are going to learn here. So let's say you have arrived at a point where you know that you need a 5 meter cube per hour flow. So if you need a 5 meter cube per hour flow, so what volumetric flow rate of pump you would be requiring? You need to transfer 5,000 liters in 1 hour. So what flow rate of pump you would be requiring?
Normal operating and maximum three flows we have. So we define for
Yes, yes.
maximum flow.
Let's say that is maximum only, because the pumps are generally designed for the maximum flow, because at least that flow should be achieved. So let's say from the maximum point of view, you need to transfer 5,000 liter in 1 hour. So you need at least 5 meter cube per hour pump so that it can transfer 5,000 kg per hour. If we talk about the density is 1,000 kg per meter cube. Am I right?
Yes, sir.
Yes, yes.
Okay. So if you are having a 5 meter cube per hour pump, you have now selected that
Please,
your
please repeat once again.
see, if you want to transfer 5,000 liter in 1 hour, so 1 meter cube is equals to 1,000 liter. So if you want to transfer 5,000 liter of fluid in 1 hour, then this is the maximum flow. Okay. So then in that case, the volumetric flow rate of pump you need is 5 meter cube per hour. Okay. So
Yes, yes, sir.
you have selected a 5 meter cube per hour pump. Now what you need to do is you need to convert that into meter cube per second. How you will convert meter cube per hour into meter cube per second? By dividing it by 3,600, because in hour you have 3,600 seconds. So you have simply converted 5 meter cube per hour into 0.0014 meter cube per second. Why you need to convert it into meter cube per second? Because what is the unit of velocities? It is in meter per second. So that's why you need, while calculation, what you need to always take care of are units. Where usually engineers fail while calculation is units. Usually they see that they are not getting answers, they are using the same values, still they are not getting answers. Why they are not getting answers? Because usually they fail converting units. Usually they took values, whatever values they are having. If I would have said you that you are having 5000 liter per hour volumetric flow rate and you need a 5000 liter per hour, I have seen many engineers that took directly 5000 here and they are writing it here meter cube per hour and they are telling that you need 5000 liter per hour. This is not correct. You need to always transfer your units, always convert your unit in SI form. Okay, so or any other form, just you need to make sure that you have all units in same standards, right? So you have converted that in meter cube per second. Now what I told earlier at the start of lecture, you might have remembered that you need always two densities, right? The density of the fluid to be pumped and the density of water to take reference. Why? Because you are seeing MWC every year, meters of water column. So for converting it into meters of water column, you need the density of water as a reference. Because why we are using meters of water column? Because generally the density of reaction mass we take as a reference, that the density of our reaction mass would be higher than the density of water. Let's say if we are using solvent, as you can see here, solvent, I have also calculated for a solvent. So here we have a density of DCM which is having higher than density of water. Some solvents are there which might be having lower densities. See, 800 kg per meter cube per hour. 800 kg per meter cube compared to what the density of water is 1000 kg per meter cube. So this 1000 kg per meter cube is taken as a reference that you are using the meters of water column as a unit. So pump vendors whenever the pump vendors will give you data sheets or will give you heads, so they will be giving you heads in meters only. So in meters of water column you have to convert that always. So for that you need the density of water and the density of fluid to be pumped. Let's say we have a density of fluid to be pumped is 1500 kg per meter cube. Okay, this is assumption for calculation. So again what you need is viscosity of fluid. Why you need viscosity?
It is the resistance to flow,
Get the resistance value.
and
Yes,
it's the Reynolds number. It has the Reynolds number is the
yes,
ratio of inertial
absolutely.
to viscous force. So Reynolds number and the roughness factor together give the friction factor component that is needed for the line sizing and hydraulics in a pump circuit.
Absolutely. So if you want to transfer a fluid from one place to another, so why you need a viscosity? Because your fluid will be completely transferring from suction side to discharge side. So you need to do a suction line sizing and you need to do a discharge side So in pump, the calculation is divided into two parts. First of all, pump suction calculation, and the second is pump discharge side calculation. So both the sides you need to calculate pressure drop. So for calculating pressure drop, which equation is used? Darcy-Weisbach equation. Everybody knows Darcy-Weisbach equation. They might have studied in the fluid
Yes.
flow operating subject.
Yes, sir.
4 FL rho V
Yes.
square
Yes.
upon 2 GD. So for
Yeah.
calculating pressure drop through Darcy-Weisbach equation, you need the viscosity. Up now you will tell the viscosity terminology is not in Darcy-Weisbach equation, but the friction factor term is there. What my one friend told, that to calculate friction factor, you need to calculate Reynolds number, right? So in Reynolds number, you have the term viscosity, right? So for calculating Reynolds number, so based on the Reynolds number, your friction factor formula will change, right? So for laminar flow, friction factor formula will be different. and for turbulent flow, your friction factor formula will be different. So once you have calculated the friction factor, then only you would be able to calculate the pressure drop with the help of Darcy-Weisbach equation. Okay, so that's why you need a viscosity of the fluids which you are transferring. Now you will say that, let's say, many industries have many chemicals which they have produced it on their own. Like means they you won't get data on internet, you won't get MSDS on internet. So if you won't get MSDS on internet, you might not be having its density and viscosity. So for calculating density, it is very easy. You can take that material. What we do, we take that material, we go into lab, we take a volumetric flask. Okay, we take a volumetric flask, we fill the volumetric flask of around 1000 ml, and we take a weight. Whatever weight is there, we divide it by the volume which we have taken. Let's say the weight is 1000 kg and the volume which you have filled in the volumetric flask is 1000 ml. So your density will be 1000 kg per ml. 1000 by 1000 means it is 1 kg per ml. So then you will convert it into kg per meter cube. So with the help of that experiment, you can get the density of the reaction mass or any mass which your organization is manufacturing, which for which data is not available on internet. But for viscosity, what will happen? How you will take the viscosity if you are not having? Same from lab itself. You need to tell the R&D engineer. As a process engineer, you need to interact with many people. Okay, so in our process engineer lecture, there also we are going to understand that how a process engineers interact with different types of departments to understand how their workflows goes. Okay, means how, what they need to get data from each department, what they need to give data to other departments. So this also we'll be discussing in the process engineering lectures. Okay, so viscosity you will be getting from R&D engineers. What R&D engineers will do? Do you know viscometer? So R&D scientists have a equipment called viscometer. So they are having spindle of different sizes. So what they do, they took a sample of reaction mass, they fill that reaction mass in the viscometer, they run at certain RPM, at certain pressures, at certain temperatures. So at that, at different temperatures, they note down the viscosity at different RPM. So you want viscosity at atmospheric temperature, let's say, and you want viscosity at higher temperature, let's say. So at 2-3 points, they provide you the viscosity. So this viscosity you can get from R&D engineers or R&D scientists. They will perform an experiment in viscometer, which is Brookfield viscometer. You can note down the equipment name, Brookfield viscometer. It is widely used viscometer in industries. So viscosity of fluid,
Why
you
not
will get.
Oswald?
Yes, Oswald is also used, but generally Brookfield have a accuracy of plus minus zero point 0.1, and Oswald's have an accuracy of zero point 0.5 plus minus. So, however, plus minus zero point 0.5 is also very less, but still industries prefer Brookfield because their maintenance point of view and service point of view, Brookfield viscometer is quite good compared to Oswald's.
With the tolerance limit of that error is
Yes,
little.
yes. Okay, so you will get the viscosity of fluid. Then you need to mention the density of water. You need to take, always note down 2 points. The suction velocity will be in the range 0.8 to 1.2 meter per second. So we have taken the mean value of 1 meter per second. And so the range of suction velocity will be 0.8 to 1.2 meter per second. And the range of discharge velocity, what you need to assume is around 1.8 to 2.2 meter per second. So this is the range you need to consider for calculation of pumps side. Okay. So what will be the suction velocity range? 0.8 to 1.2 meter per. Okay. 0.8 to 1.2 meter per second. And for discharge side, what it will be?
1.8 to 2.2 meter per second.
1.8 to 2.2 meter per second. So now you have got the suction velocity of 1 meter per second. So what you need another value is vapor pressure at operating conditions. Up now, whatever reaction mass you are transferring, you have to calculate the vapor pressure at operating condition. Let's say my operating condition is at 8 degrees Celsius. Means I am transferring my reaction mass at 8 degrees Celsius from suction to discharge. That reaction mass is having a temperature of 8 degrees Celsius. If your temperature is 50 degrees Celsius, then you need to take vapor pressure as 50 degrees Celsius. So how you will get the vapor pressure? If it is a normal chemical, you can get it from the internet. If it is not a normal chemical, then you need to perform an experiment in process safety lab. From there, you will get the vapor pressure of that chemical at different temperatures. Okay. So you need to see that graph. The process safety engineers, what they will do, they will provide you a graph where the graph will be having a vapor pressure at different temperatures. So at whatever temperatures you need the value, you need to just mention it down. So let's say it's 1.18 kg per centimeter square. In bracket it is a denotes
Absolutely.
absolute. So it is absolute pressure. Kg per centimeter square means it can be bar. 1 kg per centimeter square is equal to 1.013 bar. So it can be same as bar, right? So kg per centimeter square absolute 1.180 we have taken. Now we will start pump suction calculation. Okay. So for pump suction calculation, what we will do, first of all, we will calculate the line size of suction side. So for suction side, here line size is calculated, which we have got 42.05 mm. So how we have got this? So we have got by using Q is equals to AV. So everyone just calculate by using Q is equals to AV. Do you arrive at the same value what we have here? So you will also get the practice of how you will calculate the pipe diameter. So you have to use the formula Q is equals to AV, where Q is the volumetric flow rate, which is mentioned here. A is the area, which what is the area of pipe? It is pi by 4
D square.
D square.
d square. Why? Because it is cylindrical. Okay. So the area formula you have to use pi by 4 d square. From there you will get the diameter, and V is velocity. You have the velocity here, which is assumed as 1 meter per second. So consider the volumetric flow rate of 5 meter cube per hour, suction velocity of 1 meter per second, and just calculate the pipe diameter. Let's see who gets these values. And
Sir,
just
diameter is 0.042 meter. In mm, it will be 42.20.
yes, you will get the that units you need to convert. Okay, meter cube per hour. I have already converted it into meter cube per second, so you can use this value directly. This meter per second you have, you will get the area in meters. Then you have to convert that into mm.
Yeah. We can
So
use 2-inch
everyone,
pipe, sir.
yes. So everyone is getting this value of 42.05
Yeah,
mm
42.
value. Then you should take 1 meter per second. Then you will get the diameter in meter. And then you have to convert that meter into mm. So I think most of the people have got in mm, right? So let's move forward. So it's 42.05 mm. So now you have arrived and calculated the pipe diameter of 42.05 mm. So which size you will select? You will select 2-inch pipe, which is 50 mm pipe. Why you will select 50 mm? So you have to always select pipe based on the standard pipe size you are having. So you are having the standard pipe size of 25 mm, and you are having the standard pipe size of 40 mm, and you are having the standard pipe size of 50 mm. So You can also select 40 mm pipe here. But why here 50 mm is selected? It might be due to higher pressure drop. Okay. So generally in pumps, you need to select a one size higher so that the pressure drop will not be much higher, so that the cavitation won't occur at that side. Okay. So the 50 mm is the selected pipe diameter. You need to again convert that into meter. Why? Because you need to recalculate the velocity. Now the velocity which you have assumed, through that velocity you have got the pipe diameter of 42.05 mm.
Uh,
But
we, we don't have to match this pipe diameter to the availability of pipe like NPS or something like this. Nominal pipe sizing or whatever.
yes, that only we have done. This 50 mm pipe, I think it will be a 50 MV pipe around. So NPS you can convert it easily from the pipe size chart.
Okay.
So
It should not be low. It should be higher side. No?
yeah, it should be higher side. Based on the pipe size chart, you have to always select the standard higher pipe size,
Okay.
because lower pipe size will give you higher velocity from 1 meter per second, which will also give higher pressure.
Okay. Okay. I got it. Now I got it.
So whenever you have selected the pipe diameter, so you have to again calculate the velocity. Now onwards, whatever calculation you will be doing and wherever you will be needing the velocity, you will be using this velocity, recalculated velocity. You will not be using the assumed velocity because you have already selected the pipe sizes. Okay. Now what you will do, you will do a Reynolds number calculation. Reynolds number calculation, dV rho by mu. It's simple. So once you have calculated the Reynolds number, so you will, based on the Reynolds number, you will calculate a friction factor. Okay. So your friction factor,
For Reynolds number, which velocity we should take? 1 meter.
no, you have to take the recalculated velocity.
And for recalculated, we are using a dia 42 or 50.
No, you are
Standard
using
dia.
50 mm because you have selected the standard pipe size. Now you will calculate the recalculated. If you will calculate the velocity considering 42, then you will get 1 meter per second only, because from that 1 meter per second only you have arrived at this point. But as you have changed the diameter, the flow will be same. Dia is only changing, so the velocity will change.
Okay, so dia for Reynolds number, we take dia 50 and velocity 0.171.
0.71, right? So you have
And
calculated
density of
the
fluid.
density of fluid will be same 1500, for which you are
15.
transferring.
Yes.
Okay.
Yes, sir.
So now you will calculate Reynolds number, dV rho by mu. Now whenever your Reynolds number is less than 2100, it is laminar, and when it is greater than 2100, it is turbulent. So when it is less than 2100, you will use friction factor formula of what? Here the formula taken is wrong. Why? I will tell you.
Sir, I think we should
16 by
use
I.
64 by NRA.
Yes.
64 by
So
NRA.
yes, correct. So when you are having Reynolds number less than 2100, you will use the friction factor formula 16 upon RRE, and when it is turbulent, you will use 0.079 upon Reynolds number raised to 0.25.
Point. Yeah.
What is for turbulence, sir? Repeat the formula.
This formula 0.079 upon NRE raised to 0.25. There are also many different formulas for turbulent flow. There are Colebrook equation, White-Colebrook equation. There are n number of equations more available. So this is the simplest equation which you would be using for turbulent flow. You can also use those equations. There is not any issue in that also.
0.079 upon NRE raised to 0.25.
0.25. Right. So by using this friction factor formula, you will calculate friction
Sir,
factor.
should I
Here
use
No, here you have to use 16 upon an RE because it is less than 2100.
Should I use a Moody diagram for Reynolds turbulent?
Sorry.
If I have turbulent flow, so should I use
Yes,
Moody
yes,
diagram to find out?
you can use Moody diagram also. Moody diagram is used for white. That's what I told. Moody diagram is used for white cold. That equation is only white Colebrook equation. The Moody diagram is based on white Colebrook equation. So you can also use Moody diagram. That's not an issue. So
So
basically,
what are the difference? Is
there
there
is
any difference in
when you will
calculation?
calculate friction factors by using several formulas, you will see a slight difference in friction factor values, but there are not much difference if you will calculate the friction factor by using all these formulas which are available. If you will use Moody diagram, or you will use 0.079 upon n raised to 0.25, or you will use any other Finch equation or any other equations. So there are only slight difference, but that slight difference won't affect your pressure drop calculation.
Okay, sir.
The difference in pressure drop by calculating the Darcy-Weisbach equation will not be that much. Okay, so you can simply use that also. So once you have calculated the friction factor, what you need to do is you need to mention the static height. What is static height? It is source to pump I. Means what is the source? What is the distance of pump center to the source? That height you need to mention. Now you tell me that the base point will be pump I. Here many engineers do mistake. Okay, so what will be the static height? What will be the end point where you want height? Let's say at this point, is your vessel, this point is your pump. Okay, and this is the line distance from center to this point, and liquid is filled 50%. So you will take height up to 50% to center of I, or you will take height up to bottom of the vessel to center of pump I. What height you will be taking?
Bottom bottom of the vessel, because if I take 50% of the liquid, so when my liquid level goes down, so my NPSH will affect what I have calculated.
Okay, anybody else, any other answer or same answer?
To lower liquid level.
Lower liquid level or the bottom of the vessel?
To
So
lower
what
liquid
he
level.
told,
Bottom of the vessel. Bottom
so
of the
what
vessel.
he told
to
is,
pump I.
what he told is correct. You will take height up to the bottom of vessel. Why? Because he also gave the explanation. Because if you are taking height above, what is the NPSH formula? The static height. As you increase the static height, your NPSH will decrease. Okay, it is indirectly proportional. So you need NPSH higher. Okay, NPSH A should be higher. So